Mr. Tarrou, in this math lesson, we are going to be taking a look at the precise definition of a limit. We're going to work through three examples. The first one is a delta epsilon proof involving a linear function, the second one a quadratic function, and the third example is going to be involving an absolute value function. Now, I don't give this sort of preliminary statement in front of all of my lessons, but I've been a high school math teacher for 19 years now, and 17 years ago I was given the opportunity to teach calculus. So of course that meant a lot of dusting off of my skills and reviewing it to teach the course and prepare these lessons for YouTube. Well, over the last couple of years I keep getting comments and questions about, having a lesson about delta epsilon proofs. And one reason I would never say I'm a mathematician is proofs do not come naturally to me. I enjoy my job I love my job teaching math, and I feel like I'm hopefully good at it, but proofs are not one of my strengths. So to prepare to do this lesson, I looked at my book, I read it, I did all the problems, I looked at the solutions guide. I turned to the other teachers in my school that teach calculus, and while they're usually very, very helpful, delta epsilon proofs are not a part of any of the high school curriculum that my county uses, even the IB program. So I never covered this. And I'm doing this just for the preparation of YouTube, you guys, my YouTube viewers. So to make sure I had it nailed down, I went to a second textbook and I did all the problems there and checked the solutions guide that matched that book. And whether it was truth or my misconception of how my first book was preparing the proofs in the solutions guide that I was checking my work with, it didn't seem like they were structured the same in my second book. So to make sure I didn't present any material to you guys that was incorrect, I went on YouTube and did the same thing you guys are doing. I searched out other teachers to see how they taught the material. So between two textbooks and two solutions guides and some help with my YouTube viewers or my fellow YouTube teachers, I've developed this lesson. Now, to give them a little bit of credit, I'm going to put some links to other lessons that really helped me prepare this video in the description of this lesson. And again, I'm going to include timestamps to the three examples that we do so you can skip ahead and see any of those three examples that you so desire. And so let's get started. The definition of a limit. We're going to let f be a function defined on an open interval containing c. So we have a function, in this case increasing, may or may not have a hole here at the value of c at which we're going to define our limit at. But the open interval, they're talking about this open interval on the x-axis. And so from c, we're going to let x approach c. We have some open interval. Again, that keyword of open interval containing c, except possibly at c. So let f be a function defined on an open interval containing c, except possibly at c. I'm getting ahead of myself because I have this written off to the right here, but the idea of possibly, except possibly at c, is the idea that a limit or a function does not have to exist at a particular value of c for the limit to exist. We've already analyzed limits with a numerical and graphical approach, and we talked about how as long as the function was approaching from the left of c and to the right of c, some books call it, define that x value as a, but as long as you're approaching from the left and the right and you're approaching the same y value, that limit is going to exist. As long as the one-sided limits are equal, the two-sided limit will exist, and the function does not have to exist there. So think of a hole, removable discontinuity. And let L be a real number. Okay, so we're talking about finding the definition of a limit, the definition of a real limit. Later on, we're going to be talking about infinite limits, and that's sort of just a study of where we're going to analyze the behavior of a function as it approaches a vertical asymptote. Please remember that when you say a limit is infinity or negative infinity, you might have a function approach a vertical asymptote and go to positive infinity on the left and the right-hand side, and thus you'll say the limit as x approaches something is infinity. You are saying that there is no real limit, or the real limit does not exist, even though sometimes we'll say that a limit is infinity or negative infinity. The statement, the limit as x approaches c of f of x equals L, means that for each epsilon greater than 0, what's epsilon? I've never heard that before. Epsilon is an arbitrary vertical distance, or sort of margin of error, if you will, from the real limit. So as long as that epsilon is greater than 0, now we're going below and above, and of course if you keep your subtraction in the same order, you might be talking about, you know, a positive difference and a negative difference, but we don't see that we have subtraction on both sides of this. We're talking about epsilon and deltas as being a distance, and thus we need to have those distances wrapped in absolute value symbols to make sure that our distance is positive. I'm not concerned with trying to identify whether a point is above or below some value like you might be talking about with residuals and statistics. So as long as each epsilon is positive, as long as we're not right on the limit, you know, because the idea of limits again is approaching values, not actually being at a value. That's clear when we do our section about analyzing limits with a graphical and numerical approach, but a lot of times it starts to seem like, oh, well, find the limit as x approaches 2, and you just plug 2 in and get an answer. And so it seems like a limit is about the function's value, but it's about approaching. So as long as epsilon is greater than 0, as long as you're getting this arbitrarily small difference or distance away from the limit, there is going to exist a delta which is greater than 0. A delta is a horizontal distance from the C, a horizontal distance from the C which you're letting x approach, such that if 0 is greater than the absolute value of C. Now I'm going to again reread this in written notes, but saying that x minus C is greater than 0 is to again emphasize that x is not being set equal to 0, it's approaching 0. As long as the absolute value of x minus C is greater than 0 and less than delta. So as long as you have an x value that is within the distance of delta from C, then the absolute value of f of x minus L is less than epsilon. The value that you get from the function when you plug x in minus the limit at which you're approaching is going to be less than epsilon. Okay, well I can read that over and over again, but it might really never be clearly understandable. So let's try a different wording. You give me a vertical distance epsilon. So you pick any value for which you want to be close to the real limit of L. You give me any vertical distance E, and I will give you a horizontal distance delta. So you tell me how close to the limit you want to be, and I'm going to come over here and come down and give you a corresponding delta such that if C is within delta of x, so again, you're giving me an x which is within delta of C, or that C is within delta of x, kind of saying the same thing forward and backwards. Okay, so where was I? Give you a horizontal distance delta such that if C is within delta of x, then f of x will be within E of the limit. So in other words, let's see how. Basically, you give me basically an arbitrarily small distance of epsilon. We're going to match that up with some values of delta, and as long as you give me an x that is within C, or such that if C is within delta of x, so here's my x, and I'm going to go, you know, within this value of delta that we come up with, as long as C is within delta of x, then f of x is within epsilon of L. So you give me an epsilon, I'll match that up with a delta, and then, you know, guarantee that if I pick an x that's within that value of delta, then I will be even closer to the limit than the epsilon that you initially gave me. And so as you see us go through these proofs, what we're going to do is we're going to start off with this notation of f of x minus L and rewrite it into a form of x minus C and create a direct relationship between epsilon and delta, so that, you know, going to this idea that we have written in blue, develop that direct relationship between D and E, delta and epsilon, so that, you know, we can go back and say, well, okay, I've developed this relationship, you give me an E, I'll give you a delta, And then I can put an x within that. It gets me even closer to the limit than your epsilon you gave me. So, getting this, this is probably going to be out of in the way. Just in words written out what I've already said, I believe. You need notation 1. Let f be a function defined on an open interval. You need to be able to approach c from both sides. Basically, my understanding of that is that your two-sided limits are only going to exist if the two one-sided limits are equal. We're talking about the limit as x approaches c. There's no plus or minus here. This is not a definition for a one-sided limit. And so when you're talking about a two-sided limit, you have to be able to approach c from both sides. Notation 2, right here, except possibly at c. A function, sorry about the static, a function does not need to exist at c for a limit to exist. Again, think about those holes as the removable discontinuities. And why do we have the absolute value of x minus c is greater than 0? Even though it's going to seem like through these proofs I'm always concerned about it being less than delta, that's reinforcing the fact that x cannot equal c. Like, again, an example for those functions that have those removable discontinuities, those holes. So let's get to our first example. First example, we're going to find the limit L. Then we're going to use the epsilon delta definition to prove that the limit actually is L. And here's our first example, that linear function y is equal to 3x plus 8. We're going to find the limit as x approaches negative 2 of 3x plus 8, and then prove that that answer that we get actually is the limit. Well, we have just a line with a y-intercept of 8 and a slope of 3. We can look at the graph and easily see that the limit as x approaches negative 2 looks like it's going to be positive 2. We can do this numerically by simply plugging in negative 2 and getting again that limit is equal to 2. But again, stressing the idea that a function's limit is not necessarily the same thing as the function's value. If this was a piecewise function, maybe you could plug this value of c into the function and get an answer that really wasn't the limit, or maybe the function's existing at c when the limit doesn't exist, or maybe there was a hole, I'm pointing to where the graph used to be, where the function doesn't exist but the limit does. So we want to prove that the limit actually is equal to 2. Now, how the heck are we going to do that? With all of the delta epsilon proofs that we're going to work on, these are the steps you're going to want to do. You want to take the absolute value of f of x minus L, and which is less than, we're going to be assuming initially that it's less than epsilon, and rewrite it to match the notation of 0 is less than the absolute value of x minus c minus delta. And again, this being greater than 0 is just the emphasis that x and c are not the same value. X is approaching c. Really, you're going to see me kind of emphasizing the right-hand side here about the x minus c being less than delta. And when we get this f of x minus L expression to match this x minus c notation, that is going to allow us to create a direct relationship between epsilon and delta. In that case, in this line here, you're going to see a relationship between epsilon and delta that, because this is just simply a linear function, you can kind of see that relationship to some degree. You will at the end of the example, right there inside the linear function. Then, to actually do the proof, see, there's no way that step 1 can be the proof, because we're trying to prove that, well, we're going to find delta greater than 0 such that f of x minus L, the absolute value of that, is less than epsilon whenever, basically, the absolute value of x minus c, I don't know why I'm saying basically, but is greater than 0, but really we're emphasizing that the absolute value of x minus c is less than delta. So as long as we give an x that is within delta of c, then we're going to get a function value that is within epsilon of the limit, right here. That distance between the function's value and the limit is less than the epsilon that you gave me, that I gave you a delta that matched, and then we get this function's value that's within that epsilon. Getting the whole infinitely close idea for limits. Okay, so we're trying to prove this part. We're trying to prove that whenever the absolute value of x minus c is less than delta, that the absolute value of f of x minus L is less than epsilon. We're trying to prove that. So in step 1 where you see me start this work and I'm saying f of x minus L, the absolute value that is less than epsilon, I'm using an assumption in the beginning of this work that I'm trying to prove. So you've got to know that step 1 is not part of the proof. It's scratch work just to develop this relationship between delta and epsilon. Then we actually start the proof by saying we're going to let the absolute value of x minus c be less than that delta that we get sort of like an educated guess from step 1, and prove that the absolute value of x minus L is less than epsilon. And with the finish of that statement that the absolute value of f of x minus L is less than epsilon, then that is created our, that's finished our proof. That's saying, again, one more time, you give me an arbitrary distance, an arbitrarily small distance from the limit, and I will give you a matching delta such that if we pick an x that's closer to c than delta, then I'll move even closer to the limit than, this initial arbitrary value, arbitrarily small value of epsilon. So let's get that proof done. Okay, so we are going to, We're going to, given the fact that epsilon is greater than 0, we're going to start off with that absolute value of f of x minus L is less than epsilon. Well, our function is 3x plus 8. The limit that we found when we let x approach negative 2 was equal to 2. Oh, and I think what I'm going to do as well, this is the goal that we want to do, but let's put some notation from the actual problem so it's not quite so generic. The limit that we did find was, again, equal to 2, and the c that we're concerned about in this particular problem is, and I'm not sure if I'm going to fit this in here, is negative 2. So, I'm basically going to try and get this expression, this f of x minus L expression, to look like the absolute value of x plus 2. And if I do, then I will be able to, it's an absolute value, it's less than, an epsilon and delta. So I'll get that direct relationship. Well, 8 minus 2 is 6, so we have the absolute value of 3x plus 6 is less than epsilon. We can take a 2 out of that absolute value. The absolute value of 3x plus 6 is the same as the absolute value of 2 times the absolute value of x plus, wait a minute, I'm not taking a 2 out, I'm taking a 3. I'm thinking of the answers. So let's just change that. We're factoring a 3 out. There we go. So the absolute value of 3x plus 6 is equal to the absolute value of 3 times the absolute value of x plus 2, and of course the absolute value of 3 is just 3. So we're going to move that 3 over to the other side and get the absolute value of x plus 2 is less than epsilon over 3. Well, so I've changed my f of x minus L expression to have that matching x plus 2 on the inside. So if x plus 2, the absolute value of x plus 2 is less than delta, and the absolute value of x plus 2 is less than epsilon plus over 3, then I can say that we're going to let, or that d is, not d, delta, is equal to epsilon, there we go, over 3. And that really shouldn't be a shocking revelation that delta is going to be 1/3 basically of epsilon, because the slope of this line is 3 for every 1 unit along the x-axis. And delta is sort of, it is a horizontal movement on the x-axis from C, that the function, the slope is 3. So for every 1 unit on the x-axis you move, the vertical distance is going to change by a multiple of 3. So if you want to put it in terms of delta, delta is the horizontal distance along the number line is 1/3 of epsilon. Now, you're not always going to be able to see that because, well, not your problem. Many of your problems are not going to be linear functions, but there's that relationship. Now, what you want to do is, this is our scratch work. This is that direct relationship between delta and epsilon that we were talking about. So now, just want to make sure I don't write this the wrong way. You want to actually start the proof by writing this. For every delta greater than 0, let delta equal epsilon over 3. And 0 is less than the absolute value of x minus -2, which is less than delta. Or just the idea that we're going to be letting the x approach that -2. So you can write x minus -2 or just simply x plus 2. Now, again, our goal is to prove that f of x minus L is less than epsilon when you have this relationship that delta is 1/3, equal to 1/3 of epsilon. So we're going to start off with, so we have f of x, which is going to be, I'm pausing because I realize I'm not going to have enough room to write all this. F of x is 3x plus 8 minus our limit, which is equal to 2. And I'm not going to write that that's less than epsilon. That's what I'm trying to prove. So let's see what we got here. We have 8 minus 2, which is going to be, of course, 6. And actually, I want to pause here for a second. Let's say that this expression is our absolute value of f of x minus L. I want to just have that written there so we have it to reference at the end of our proof. So the absolute value of x minus L is equal to the absolute value of 3x plus 8 minus 2. 8 minus 2, of course, is equal to 6. We can take the, now this is equal to, now we have our 3x plus 6. We're going to take out our factor of 3 and get x plus 2. And this f of x minus L is still equal to that expression of 3x plus 2. But now, see, for every delta greater than 0, let delta equal epsilon over 3, and the assumption that we're going to be picking x as x minus 2 is less than delta. So I can bring this in here and now say that this expression is less than 3 times delta, because it says right there, and absolute value of x plus 2 basically is less than delta. Well, delta we have set up to be equal to 3x, or equal to e over 3. So now that is, now this inequality is going to be in reference to our absolute value of f of x minus L. So that is going to be less than 3. Hope my next problem doesn't have 3's and e's together. 3 times delta, which we set, we're setting equal to epsilon over 3. And of course, you know, multiplying by 3 and dividing by 3 are going to cancel out, and we have that when those cancel out, we have less than epsilon. So we have proven that the absolute value of f of x minus L is less than epsilon when we have this direct relationship between delta, which is equal to 1/3 epsilon. That direct relationship we got from our initial scratch work, getting our f of x minus L expression to match that x minus c expression. And that's the end of our first proof. So that's saying that as long as you give me an arbitrarily small distance of epsilon, I can give you a delta which is 1/3 the value of epsilon. And then when you give me, when I come up with an x that's inside that delta, which is 1/3 epsilon, I can give you an x, go to the function, and get a value from that function that is within the distance of epsilon to the limit. And that is the end of our first example. Bam! Except, I want to point out though, that initial confusion that I had from working all these problems in one calculus book and looking at the solutions guide, and then, like I said, going to another book and then going to the YouTubes and getting some additional references to help develop this lesson, I will show it to you. I saw some proofs where, especially with these simpler examples where the functions are just linear functions, where this actual structure of the proof was kind of like in reverse. Some people started off the proof with this statement, 0 is less than the absolute value of x minus c, which is less than delta, and then worked backwards until they got a value or statement that f of x minus L was less than epsilon. I guess I can kind of see how that flows for the simpler examples, but when we get to our second examples dealing with an epsilon delta proof involving a quadratic, I think that doesn't really flow very well. So I'm going to show all my examples in this fashion, where we start with that f of x, that absolute value of f of x minus L statement, and prove in this sequence ultimately that it is less than epsilon using whatever direct relationship we come up with in the problem. So before we move on to those last two examples, I wanted to show you how I initially did all of these proofs. And it did kind of bother me the way this worked. We would take our limit statement, find the limit, again say that given that epsilon is greater than 0, start with our sort of preliminary scratch work. The absolute value of f of x minus L is less than epsilon. Work it again till we got that, match that x minus c is less than delta expression to get that direct relationship between epsilon and delta, and then make a statement that if we choose delta is equal to 1/3 x, then if 0 is less than the absolute value of x minus c, or in this case, of course, -2, is less than delta. And the proofs, again, kind of worked backwards to the maybe slightly clearer way that another textbook solutions guide was showing theirs, and how I saw people on YouTube working out these epsilon delta proofs, especially with the more complicated examples involving something like, say, quadratics or absolute value functions. And I think, so with my experience, or maybe lack of experience with these epsilon delta proofs, I'm not really sure which way is better. I don't really think this is the better way. Again, I found examples on these simpler epsilon delta proofs in my book and online, or at least what I interpreted my book was saying, and online, showing some people showing these sort of working in reverse, and then getting down to the absolute value of f of x minus L is less than epsilon. It doesn't really sit well with me, knowing how I structure my trig proofs when I work those out with my pre-calculus or trigonometry class, and it certainly feels like it leaves the door open for some confusion when dealing with examples like that are coming up next, finding or working with an epsilon delta proof involving a quadratic. And getting on to that quadratic example. Find the limit, then use the epsilon delta definition to prove that the limit actually is that L, that real limit that you believe it to be. We're going to find the limit as x approaches 5 of x squared minus x minus 6. Okay, well, let's just get the limit out of the way. The limit as x approaches 5 of x squared minus x minus 6, well, I kind of gave it away there, is going to be equal to 5 squared minus 5 minus 6. Well, that's 25 minus 5 minus 6, which is going to be equal to 14. So we're going to try and prove that the limit of this expression is 14 when x approaches 5. And we're going to do that like the last one. The first thing we needed to do is some scratch work to develop a direct relationship between the variables of epsilon and delta. And we're going to do that again by starting off with this expression here. F of x, the absolute value of f of x minus 14 is less than epsilon. and rewrite it into this format where we have the absolute value of x alone, and then on the right hand side it's less than something, and we'll hopefully get that direct relationship between epsilon and delta like we had the last one. So we have the absolute value of, oops, dropped this chalk earlier, now it's all busted up. The absolute value, our function is x squared minus x minus 6, so there is our f of x, minus the limit that we found to be 14. That probably should have been L there originally. And then fill it in. That is going to be initially in our scratch work assumed to be less than epsilon. We're really trying to prove that in the end. Combined like terms, we have the absolute value of x squared minus x minus 20 is less than epsilon. That left-hand side is factorable, and when you have a expression inside of an absolute value symbol that's factorable, you can still factor. Just make sure you leave each of those factors in their own absolute value symbol. So we have the absolute value of x minus 5 times the absolute value of x plus 4 is equal to epsilon. Trying to isolate that absolute value of x minus 5 and manipulate that original f of x minus L statement to match the x minus c expression like we did in the last problem. We divide both sides by the absolute value of x plus 4. That should be a minus sign. Okay, well, we can see now that there is a problem with this. Ooh, and I forgot my given that epsilon is greater than 0. I'll sneak that in a little bit neater later. We can see that we do not, yes, I have the absolute value of x minus 5 by itself, but less than delta, less than epsilon over the absolute value of x plus 4. We don't have a direct relationship between these two variables, and we need that to, do our proof. Oh man, okay, how the heck are we going to do that? Well, we need to remember that, we're finding limits. We're trying to let x approach c. In this case, that c value is 5. We're trying to let x approach 5. So we don't need to be 10, 15 units away from 5. We want to let x approach 5. So to create a direct relationship between delta and epsilon, we need to eliminate this absolute value of x plus 4, at least rewrite it in a form that doesn't have a variable in it. So what we need to do is set a limit on delta, set a maximum distance from the value of c, some books call that a by the way, that we're willing to use for the proof, put a condition on it, and then we want to find the maximum value that this absolute value of x plus 4 is going to take on. So just a little diagram. I just took my quadratic, put it into standard form or vertex form or whatever it is your textbooks called it. Have a sketch here, and again, just trying to show you that, again, the delta being a horizontal distance away from c, we're going to set that to be a maximum of 1. I'll write all that out, and then from that idea of making sure that the absolute value of x minus 5 does not take on or compare to a delta that's greater than 1, get some kind of relationship, some kind of maximum value that the absolute value of x plus 4 will take on. So just writing out what I said, we need that direct relationship between epsilon and delta. Now, if we do maximize that delta or allow it to be only a maximum of 1 or smaller, we have delta is less than or equal to 1. And we're going to, again, whenever the absolute value of x minus 5 is less than delta, from that statement we have the absolute value of x minus 5 is less than delta, and then setting that to be a maximum of 1, we have x minus 5, the absolute value of x minus 5, is less than 1, and I wrote it as a compound inequality because of, obviously, a lack of room. I'm trying to get all this example up here at once. We need to rewrite that x minus 5 expression to you know, into the form of x plus 4, again, to see the maximum value, to find the maximum value that that will take on. So we add each of these three parts of our compound inequality by 9, getting the x plus 4 that we need, and while we can see it is greater than 8, we're trying to find the maximum value that x plus 4 can take on, and that is going to be 10. So from that we have the absolute value of x plus 4 is going to be less than 10. So from this, I can come over here and write one more line. The absolute value of x minus 5 is less than epsilon over 10. So now from here, it would seem that we could let delta equal epsilon over 10. But for the rest of this proof, you know, is it really acceptable to say that delta is equal to epsilon over 10? This isn't as simple of a direct relationship as it was with the linear function, of course. I had to work on a limitation on delta to get that direct relationship. So because of that, we're going to say that delta is going to be equal to the minimum of 1 and epsilon over 10. Again, with this extra condition now put on this, what I'm going to say is my direct relationship between delta and epsilon, is it going to be acceptable for me to replace anytime I see a delta with epsilon over 10? Well, if delta is equal to epsilon over 10, then based on this condition, that means that epsilon over 10 must be less than 1. And since delta is the minimum of these two values, we can go ahead and say that we've got, with the idea that starting off with the absolute value of x minus 5 has to be, again, whenever that is less than epsilon, then the absolute value of x minus 5 is going to be less than epsilon over 10. Close up that absolute value symbol. Okay, let's keep that in the back of our minds as we work through our proof. What if we have the condition where delta is equal to 1? That epsilon is given in such a manner that has this fraction be larger than 1. Well, again, we only came up with that expression, that direct relationship, delta is epsilon over 10, with the condition that delta can be no more than 1. So if delta comes out, if we have to set delta equal to 1, well then that means that 1 had to have been less than the value of epsilon over 10. Okay, so again, with this idea that starting off with find delta greater than 0 such that the absolute value of x minus L, or in this case 14, is less than epsilon whenever x, the absolute value of x minus 5 is less than delta. So if we have the absolute value of x minus 5 is less than delta, which we're saying is 1, we're saying that it's 1 because the epsilon was such that this fraction came out to be bigger than 1. Well, I would still like to be able to know that when I see an epsilon, an absolute value of x minus 5, that I can relate it to this epsilon over 10 idea. Well, if we picked 1, then 1 was less than epsilon over 10. And if the absolute value of x minus 5 is less than 1, because we had to set delta equal to 1 because it was bigger than, or excuse me, smaller than e over 10, well then it's also less than epsilon over 10. I just said e. So that means that we can clean this up and say, well, if absolute value of x minus 5 is less than 1, which is less than epsilon over 10, then it is just simply the absolute value of x minus 5 is less than epsilon over 10. So I can still, write that statement that letting d be equal to epsilon over 10, that direct relationship we got by setting delta to be a maximum of 1, has to be less than or equal to 1, either way, whether the delta is going to be set equal to epsilon over 10, or if d is equal to 1, with that condition that the delta is the minimum of 1 or e over 10, it's still acceptable to write the same statement that the absolute value of x minus 5 is less than e over 10. So now we are ready to start our proof. So officially starting the proof, now that all this scratch work is done, for every epsilon greater than 0, let delta equal the minimum of 1 or epsilon over 10, and let 0 be greater than the absolute value of x minus 5, which is less than delta. Now with these conditions, we are trying to prove that the absolute value of f of x minus L is less than epsilon. So we have the absolute value of, again, f of x is minus the limit L is equal to, the function again is x squared minus x minus 6. Our limit that we found it to be when we plugged in 5 came out to be 14. And can I manipulate this expression and show that ultimately this is less than epsilon? So this is going to be, just like before, the absolute value of x squared minus x minus 20, which is equal to the absolute value of x minus 5 times the absolute value of x plus 4. And now we start working with these relationships that we just came up with. We were able to show, or actually not show, but we have the initial assumption that the absolute value of x minus 5 has to be less than delta. We're trying to prove that the absolute value of f of x minus L is less than epsilon whenever this is true. So this now, this is going to become, I don't have room to write it over there, less than delta, and the x, I don't know why I'm using parentheses, the absolute value of x minus 4, we have from our scratch work over here that the absolute value of x minus 4 is less than 10. Okay, well, we're trying to prove that this is less than epsilon, so we need to get the delta out and replace it with an expression that has an epsilon in it. And we just happen to have it right there, and we were able to validate with our checking our work here and working with this extra condition that we created, which was that delta can be no more than 1, that every time we see an absolute value of x minus 5, yes, that's less than delta, but we can also have shown that it is less than epsilon over 10, which we've set equal to be delta. And now we can see that the 10s are going to cancel out. And bringing this down now, we have the absolute value of f of x minus L is indeed shown with these conditions that it is less than epsilon. So by definition, so therefore, or a box, or whatever your book is using, by definition, the limit as x approaches 5 of x squared minus x minus 6 is indeed equal to 14. And that is the end of our second example. Now before we move on to our last example, which is going to be an absolute value function, I wanted to put some concrete arithmetic, some examples that go along with this proof. Not validating the proof is true, because you can't do a proof with just examples, but show you some examples on how they relate to what we said in this proof. That if delta is the minimum of 1 and epsilon over 10, and we are looking for x approaching 5, we're letting the absolute value of x minus 5 be less than delta. We showed that the absolute value of f of x minus L is indeed less than epsilon, but that idea that you give me an arbitrary epsilon, and then from that I'll develop a delta such that if x is within delta of c, that when you plug that x into the original function, you get the difference between the function's value and the limit, which is less than epsilon. So let's let epsilon be equal to 20. If that's the case, then delta is the minimum between 1 and epsilon over 10. Well, if our vertical distance from the limit is set to be 20, then 20 over 10 is going to be equal to 2. So in that case, see, our epsilon over 10 expression is indeed bigger than 1. It's 2, but we're letting d be the minimum of 1 and epsilon over 10. So we're going to let delta be equal to 1. Well, in that case, delta being the horizontal distance from C or A, however your book is denoting that, and we're finding the limit as x approaches 5, then C is 5, and C minus delta is 4, and C plus delta is 6. So picking an x that is within delta of C, let's let x be 4.5. Well, if we let x be 4.5, f of x, f of 4.5 is 9.75, and the absolute value of fx minus L, is it indeed less than epsilon? Well, is the absolute value of 9.5 minus 14 less than 20? Yes, it is. Now, if we pick an epsilon value, again, that vertical distance from our limit, that's 1, that's smaller, if we let epsilon be 1, then we have, again, d is the minimum between 1 and epsilon over 10. Well, if I say epsilon is equal to 1, then d is a minimum of 1 and 1/10. So since d is the minimum of one of these two values, delta, I keep saying d all of a sudden, delta is going to be set equal to 1/10. Well, again, we're finding the limit as x approaches 5, and moving to the left and the right of 5 by a delta of 1/10, we get c minus d delta is 4.9 and c plus delta is 5.1. We need to pick an x that's within delta of c, or that c is within delta units of x, and so we're going to let x be 5.05, somewhere within this interval. Well, if you take 5.05 and you plug it into your function, you get a value of 14.4525. And indeed, or with this example, is the absolute value of f of x minus L less than epsilon? Well, f of x, again, just set it out of the calculator, 14.4525. The limit is equal to 14. The absolute value of this comes out to be 0.4525, and that is less than our epsilon, our given epsilon, or arbitrary epsilon of 1. So there's some arithmetic examples to go along with what exactly these proofs are telling us and how they work. Bye. Last example. Find the limit, then use the epsilon delta definition to prove that the limit is actually L. This time we have an absolute value function. We're going to find the limit as x approaches -7 of the absolute value of 2x minus 14. So where's my chalk at? Here we go. Well, I got lots of chalk, but the one in the holder. We're going to let x approach -7, and that means that we're looking at the absolute value of 2 times -7 minus 14. That is going to be the absolute value of -28, which of course we know is equal to 28, because the absolute value function tells you how far a number is away from 0 on the number line, even though we just always say it gets rid of the negative. Now, one thing to take a note of as we do our proof is to pay attention to the idea that when we let x approach -7, the absolute value signs had to change the sign of our answer because, well, 2 times -7 minus 14 came out to be a -28. So we had to change the sign to get the limit. And we see the graph is here, and here's our -7. And we're approaching that y value, that limit of 28. So again, we're going to say, given that epsilon is greater than 0, that the absolute value of f of x minus L is less than epsilon. Again, assuming that to be true as we work out the relationship between delta and epsilon. So one last time, this is scratch work. This is not the beginning of the proof. So the absolute value, our function, is, again, the absolute value of 2x minus 14 minus the limit that we found, which was 28, is less than epsilon. Okay, well, we have an absolute value inside of an absolute value, and how are we going to get this expression to look like, oh, yes, let's change these notes. Well, I really meant to write x minus c there, but I was going to change it into terms of this problem anyway. Find delta greater than 0 such that f of x minus 28, the limit that we found it to be, and we're trying to prove that it is less than epsilon whenever 0 is less than the absolute value of x minus a negative 7, or effectively just x plus 7, is less than delta. So how do we get this expression with an absolute value symbol in it to look like just simply x plus 7? Well, this is just right already where we need to take into account the idea that what happened, what did the absolute value symbol do when we tried to find the limit as x approached negative 7? It changed the sign and made, negative 28 basically be positive 28. Well, what math notation do we use, or what math operation can we use to change a sign other than just, well, it's not the same as absolute value symbol, of course, but if you want to make a negative number into a positive, you multiply it by negative 1. So understanding that as x approaches negative 7, that this is going to be a negative answer, that 2x minus 14 is going to be, okay, I'll write that better later, less than 0, that absolute value is going to change the sign of that expression or that answer. So we can replace the set of absolute value symbols with a set of negative parentheses. So the absolute value, not all the time, but just for this particular problem with x approaching negative 7, we have the absolute value of the negative parentheses 2x minus 14 less than or minus 28 is less than epsilon. Distribute the negative through, and we get the absolute value of negative 2x. That's going to be negative times negative is positive. I'm not sure why I'm pausing there. Plus 14 minus 28 is less than epsilon. Now we have the absolute value of negative 2x minus 14 is less than epsilon. This is going to be the absolute value of negative 2 times the absolute value of x plus 7, because negative 2 divided by negative 2 is 1, and negative 14 divided by negative 2 is positive 7 is less than epsilon. This is going to be, the absolute value of negative 2 is 2, so we have, bringing that over to the other side, we have, I just want to make sure I don't run out of room here, the absolute value of x plus 7 is less than epsilon over 2. So we have basically x plus 7 is less than delta. We have x plus 7 is less than epsilon. Really understanding how to deal with that absolute value symbol. Now, if we were finding the limit as x approached, I don't know, 5 or 6 or 7, or somewhere to the right of that sharp bend where the absolute value sign function didn't have to change the sign of that value, then we would just drop those absolute value symbols altogether. But in this case, we needed the negative parentheses. And dealing with that, we get right off the bat a nice direct relationship between delta and epsilon, a little bit easier than it was in our previous example dealing with the quadratics. So we're going to let delta not d, but delta equal epsilon over 2. And now we are ready to start our proof. So the proof is for every you know what? I know I'm going to have to cram this in here. Epsilon greater than 0, let delta equal epsilon over 2, and 0 is less than the absolute value of x minus negative 7, which is less than delta. And I have the statement up here, but I really don't want to have this start to flow, and I hate proofs that kind of go all over the place. So let me step off, erase all of this, and clean it up, and put this proof statement at the top of the board. That's better. I wanted to have all this on the board so you could pause it at the end and see everything together. So again, our proof for every epsilon greater than 0, let delta equal epsilon over 2, and 0 be less than the absolute value of x, basically plus 7, which is then less than delta. And with those conditions, again, we're trying to, whenever these conditions are met, that the absolute value, we're trying to prove that the absolute value of f of x minus L is less than epsilon. So let's start off with that one last time. Absolute value of f of x is less than L. That is equal to the absolute value of 2x minus 14 minus our limit that we found to be positive 28. That is going to be equal to, just look very similar to this work over here, or over there, the absolute value of negative 2x minus 14 minus 28. That is equal to the absolute value of negative 2x. Distributing the negative, we have, again, positive 14 minus 28 is negative 14. Factoring out that negative 2 and writing the absolute value of negative 2 is not just completely factoring out, but separating this one absolute value statement into two absolute value statements. The absolute value of negative 2 times the absolute value of x plus 7, or x minus a negative 7. Now the absolute value of negative 2 is equal to positive 2, and the absolute value of x plus 7, we showed that the absolute value of x plus 7 was, where is it at? Oh, right here. The absolute value of x plus 7 is less than delta. So, less than, excuse me. So this expression, this absolute value of f of x minus L is equal to this, and this is less than the absolute value, if you want to leave that in there for a second, the absolute value of negative 2 times delta, because x plus 7 is less than delta. So when I replace that absolute value of x plus 7 with delta, well, that is less than delta, so this entire expression is less than absolute value of negative 2 plus times delta. Okay, so now at any rate, the absolute value of negative 2 is, of course, just 2, and delta, we found that direct relationship between delta and epsilon to be delta is equal to epsilon over 2. And like before, thankfully, these values of 10, or in this case 2, or whatever it was in the previous examples, we're canceling everything out until we get just an epsilon. And we're right back to, thankfully, again, finishing our proof and validating the statement that we found that the limit as x approaches negative 7 of absolute value of 2x minus 14 is 28, because with these conditions in this proof, we have that the absolute value of f of x minus L is indeed less than epsilon when we have the 0 is less than the absolute value of x plus 7, which is less than delta, and that delta has this relationship with epsilon, which is going to be half of whatever epsilon is. So by definition, we have the limit, I'm just going to write what I said a second ago, as x approaches negative 7 of the absolute value of 2x minus 14 is indeed equal to 28. And that is the end of my last third example. I'm Mr. Tarrou. Go do your homework.